So the second chapter is about to produce some fundamental signals, but how to actually work on system fundamentals. Again, this exercise, the first exercise part, I think the first 3 exercises we'll go through together, and the rest of those you can work yourself. Let me open that slideshow again. Okay. So slideshow, again, DSP theory, a brief summary. Basically, the digital signal processing operations are very simple. Only 4 of them available. So we have addition, which is simply 2 signals addition, and block diagram symbols are either the plus or oh, wait a minute, I have this nice tool here. So it's either the plus sign or then this the sigma operation. The second is scaling a signal, so it's basically like amplification. You multiply a signal with constant. Then the third operator is delay operation, and mathematically it just is you have the offset in index, nothing more. You're just shifting the data, either forward, meaning the delay, or the backward, meaning the advance. The block diagram symbols basically are, there are 2 different symbols there in use. One is z to minus k, which basically takes you into the z transform space. Nothing to worry about that one. I will tell you more about that tomorrow. The other one is basically just how many time delays, k times d. For example, you have 4 times time step delays, then either 4d or 4 times d. Then the fourth operation is multiply of signals. So this is same as the modulation. Nothing more. So those 4 operations, and that's it. Then of course you can put these wires all around the place, so which makes it interesting. The multiply of signals, basically we don't cover that one on this this course at all. But as a curiosity, multiplication of signals could be done, for example, your sinusoid generation. So if you have a sine wave generation here as a signal, and then you have the envelope with this ADSR block. So attack, decay, sustain, and the A, D, sustain, and release. Envelope. So adding an envelope to a sinusoid actually would make different kind of synthesized sounds. The same as your grandfather did with their moods. Grandmothers didn't have moods, sorry. That was the old days, and they were not better. Yeah, okay. So Star Wars 1 basically had the Moog people doing the sounds, in addition to the people who were doing sounds by their mouth, and all kind of like the. Have you seen this is a really nice documentary how they made the sounds for the Star Wars 1, 2, and 3? That's actually quite nice. The sounds are mostly analog actually, like the TIE Fighter. It's they took a wire to the window and then started scratching it with styrofoam. Yeah. Digital, yes, sure. Yeah, the old ones, the originals, the episode 3 to 6, yes. But on episode 1, they all had digital effects. I don't know which one was better. All right, so okay, back to this topic, properties of systems. Okay, in principle you should be aware of these from some other courses. Linearity of a system. What does it mean? Basically, it means that you can break up the signal into parts and put those parts through the system. It's the same as running the whole signal at once. So superposition principle. It's nice. It's a good property actually for for most of the systems, since then you know exactly what is going to happen. Unfortunately, there's no such thing as a totally linear system. It is linear only within some region, with some limits. For example, your car. How many of you have a car? Do you have your own cars yet? Yes, you have. And you have the car stereo always at point 11, right? It's not linear anymore. Your car radio is probably at the 40% or so volume. Then it operates linearly. If you hit the saturation, basically, even if you add some more signal, it doesn't go higher than that. So it's not linear anymore. So basically, linearity means that if you add something, you show also the results of that addition on the output. Okay. Causality. Don't mix this one with casuality. You know, casuality is like you with a t-shirt. Okay. Causal means there must be some reason for the output. So there's no effect before action. So basically, causal, yeah, causality means that you know that, okay, if I drop a pen, it makes a sound, but it doesn't make the sound if I don't drop it, or it doesn't make the sound before I drop it. Okay. Stability. Stability in our system means this kind of bounded input, bounded output stability, which means that, okay, again, these stereos, if you have limited signal, then you know that it doesn't saturate. That's a stable system. Fourth one is the time shift invariance, which basically means that the system does not the system behavior does not depend on time. Good example of non-time shift invariant system would be parking meter. On daytime, you must put some coins on it. Nighttime, you don't need to. So it changes the behavior of the system. But otherwise, for example, cars, it would be nice to have time shift invariant system. Right. So it will probably start the same way if it's morning or evening. When it gets old, unfortunately that's not anymore true. Okay, but anyways, these properties of the system, they are not about good or bad mostly. It's about just the, property. It's just a property. Okay, let's talk more about this linear and time shift invariant system. If we have a linear and time shift invariant system, then basically there's a claim that you can actually show the system output as weighted sum of time-shifted inputs and time-shifted outputs. Meaning, practically, let's see, do I have, yeah, that you can describe the whole thing using that kind of difference equation. I don't like my graphics here, but basically it's just the this one here. There are weighting factors A for which are multiplying the output and its history. Okay, there's yn is the current value, like in here. So this is the current value what we are calculating. We call it y of n. Then we have this feed forward section, which is the this B the scaling factors, which are constant scaling factors for this system, multiplied by different delayed input signals, minus the remaining part of that one, which is the history of output. So this is the feedback term, this is feed forward term. And the minus is not an accident, it comes from that back. So difference equation is defined like that. So everything is of the output is on one side and another, everything else input is on the another side. But this is kind of way how you usually describe it or start figuring out from a block diagram. Okay. Example, the simplest filter which is actually, simplest filter of all is a running average filter, meaning that if you have some data, let's take the data. Data, x of n sampled at those points, So basically the output of yn is calculated these values will give that the average of these four values will give here one signal or one sample y4, and then y5 is calculated from the next 4 points, just the average of 4 subsequent samples. And that's the 4-point running average filter difference equation. However, you can also calculate the same thing using feedback. Since basically when you are taking the average, then the next average, you will leave these values and drop one out, or wait a minute, the other way around. The oldest value will be dropped out and the new one will be coming in. So that's kind of recursive way of calculating this running average filter. And formula looks like that. So you have the previous output with the previous the 4-point average like in there. So it's y4, and here the y5 is actually you have this y4. Then you basically add the current value 1/4 times x of 5 minus 1/4 of x of 1. The oldest value goes out, newest value goes in with the weight factors, and then you have the previous value. Or actually like that. So what is the difference actually on the first one and the second one? Well, for me, it seems that there's less calculations. It's more efficient to calculate like that. Think of, for example, 100 points running average. That will always have that number n there. So 100 times addition to actually, well, 99 times addition, and then the scaling, compared to only 2 additions with the same scaling. So which one is more cost efficient? Well, of course, here using feedback. Okay. So that's the difference equation. So basically, difference equation is formula to calculate the output, although that's not the formula to calculate the output, because we have the block diagram. Block diagram is the implementation. Think of the microcontroller, how you would like to make these calculations. So would you like to do it like this, meaning that you multiply each of these input variables separately and then add them? Probably not. Probably you would like to have a common multiplier at the beginning, and then you have the delays like that, and then additions like that. That looks like more cost efficient than this one. It's better to scale the product, scale the values when you're coming in, if there's a common scaler here. So once you have scaled, you are using the previous values here. So this is the buffer for the previous values. Or something like that. Scale the input, and then you have the 4 times step delay here. Okay, and you minus. Okay, so basically this is the way to do that feedback version of the running average filter most cost efficient way. Although, okay, that Z to 4 requires one more memory element. So here we have 5 memory elements compared to 3 memory elements here. Okay, but we are down to 2 additions compared to 3 and 1 multiplication. Easy. So this block diagram is the way to implement the difference equation. Good. Then the hard part. Hardest part probably from this course is the transfer function. Have you got some automation technology classes already, or something similar? Have you been bouncing to the transfer functions this far? At least on analog electronics you have, and you probably have actively forgotten them, because that's not easy. At least that's what I did. All right, so a transfer function is, well, that's the couple of definitions there. On continuous time system, you use Laplace transform, and everybody hates that one. At least I do. But anyways, that's one way of figuring out how the system works, or basically comparing your theory with the real life. On continuous time systems, you can actually calculate the what is the output for given input if you know the Laplace transform of the input and transfer function of the system. Yeah, the same thing also in discrete time, but fortunately we don't need to go and do the Laplace the Z transforms that often. It basically we need to do it only once. Okay. Why we need the transfer function actually comes together quite well with the convolution. Remember the convolution. Convolution is the way to filter. So basically, we do a frequency space multiplication by convolution of the signals. So that's the Z transform of any input signal. The Z transform of impulse response is the same as the transfer function. So basically, convolution comes down to this. So basically, the convolution is the filtering operation. Okay, some properties. Okay, those are the mathematical kind of properties. One is that it's linear. Then another one is the time shift, how it actually relates to that one, and then unit impulse goes to delta function, transforms into 1, and the step function transforms into Z divided by 1 plus C. Nothing much to see here. Okay, but if we had a linear LTI system with given the difference equation, we can actually see from this that our system coefficients are actually exactly the same in time domain and frequency domain. Meaning, okay, think of the AK Y n minus K difference equation. BK H n minus K. Oh, by the way, the block diagram for this kind of system would look like, let's go. We have B0, B1, B2, and so on this side. And on the output, we have Y of n, and then we have the feedback part with multipliers A1, A2. So same indexes there than there on 1. A1 multiplier is 1. There. Okay, so block diagram, difference equation. Z transform both sides. It's still equal because we have a linear operation, right? Meaning that we have Z transform that one. Linearity means that you can actually get these scaling factors out, and we have AK times Z transform of Y minus K equals to BK Z transform of Xn minus K. There's a time shift operation, meaning that Z2 works, for example, Xn minus K is the same as Z2 minus K times Z transform of X of n. There we go. So that actually goes into AK times Z Z to power of minus K times now we have this one as a common multiplier. So that one go out. I'll take the other one already here. Oh, sorry, not X, Y. Well, X n minus K, no, any minus K. I take it out. It's basically times sum BK times Z to minus K. And my transfer function was defined basically so that it's the Z transform of output divided by Z transform of input. Right. So how about dividing that one there and dividing that one there? We have on numerator bk times Z to minus K. Denominator is AK times Z to minus K. Ah, wow. Okay. So basically, if a system coefficients, the scaling factors on this system are A and B, or actually B and A. So that's B. This one here is A. There's a multiplier of 1 here. Then it defines both the formula of how to calculate in time space, and also those same coefficients also define the system in frequency domain. Okay, not bad. Wow. So, for example, the 4-point running average filter. Here we have the formulas for the 4-point running average filter, which is simply basically 1/4 times 1 plus Z minus 1, Z minus 2, Z minus 3. So yes, so basically, if you compare this one with the how does it go? So our the difference equation for okay. So in this formula we have, this is B0, okay. So shall I use some other color? This is B0, this is B1, B2, B3. So those are the coefficients directly. Okay, and then the denominator coefficients, here we have A0 is actually that 1 in front of the y of n. Okay. This is then exactly the same as, or actually this one here for the running average filter. If you take that form of running average filter transfer function, multiply and divide it by 1 minus Z to minus 1, you will get the feedback term transfer function. Okay, where we had x of n plus x of n minus 4. And on feedback, we had that plus the previous, which basically here is minus z minus 1. Good. And now we have the Nullstellen und Polstellen. Haha. My first two words that I learned from German. Nullstellen or Polstellen. Okay, this is actually, transfer function actually is a nth order polynomial, rational polynomial. Nothing to be very afraid of. It's just polynomial. Numerator polynomial divided by denominator polynomial. If we actually multiply the upstairs and downstairs by z to n, well, the z is actually the n is the highest order in this polynomial, we get actually something like this: b0 times z to n plus b1 times z to n minus 1, and so on until we hit the plus b of n. Same thing here, a of 0, a0, z to n plus plus a n. Those are positive index polynomial, meaning that it has roots. Polynomials have roots. Numerator polynomial roots are called Nullstellen, zeros. And roots of the denominator are called Polstellen, which is poles. So zeros and poles actually are just the special points of transfer function. Zeros are the same as when the transfer function goes to 0 when the numerator polynomial goes to 0. Transfer function goes to haywire when the denominator polynomial goes to 0. It's not defined on those places. Okay, so you basically can calculate the roots, and after you have calculated the roots, zeros and poles, then you can actually have the product form of this transfer function. Product k from 1 to n, k from 1 to n. There we have z minus zk. These are the zeros, and c minus pk. These are the poles of the system. It's just marking, which helps us determining, for example, if the system is stable or not. Yeah. For example, here I have some zeros and poles. Sorry, this plot is a little bit off. I should replace it at some point. So those poles are marked usually by crosses, and zeros are marked by circles. Those zeros on this picture should be actually on the unit circle, but well, graphics basically is a little bit off. Well, but anyways, it's a zero pole plot, which is also called as Argand's diagram. Argand's diagram. And basically, let's see. Yeah, okay, I have marked there Z1, Z2, Z3, Z4, P1, P2. And then there are two poles on the origo. Real axis, imaginary axis, unit circle. Multiple poles, yeah. On Argand's diagram, the system gain is marked there on the separate place, but these, what are these? MATLAB or Octave functions, it's usually not marked at all. Okay, but an example again. 4-point running average filter have this the product form of that the transfer function is here. No, not product form, but the positive index. So you have z cubic z square z1 plus 1. When you put this one to 0, you get those as the roots of that polynomial. Minus 1 I plus I. Any of those values will give you 0. So those are the locations of minus 1 minus I plus I. Poles, okay, meaning that z to the third exponent goes to 0, meaning that you have triple pole at the origin. Okay, remember, now we are dealing with the complex numbers. So if you are nth order polynomial, it has exactly n roots. All right. And then the stability. The stability of a digital system depends on the location of poles. The same as analog systems. The S-plane poles should be on the left-hand side of the S-plane, right? On the right-hand side pole, then the system is chaotic or unstable. So if even one pole is outside of the unit circle, then the system is unstable, meaning that it's useless. It'll saturate in a second or less. If the poles are inside of the unit circle, then it's stable. If they are on the unit circle, then we call it oscillator, meaning critically stable system. It has gain 1 for that frequency. Zeros can be anywhere. For stability sense, they can be anywhere. But poles must be truly inside of the unit circle in order to have a stable system. Which means that, for example, this one is stable, of course. All the poles are on the origo. This one is also stable. All the poles are inside of the unit circle. Good. That was a heavy package of theory. Let's go back. So simple operations: add, scale, delay, multiply signals. Some basic fundamental properties of the signal system: linearity, causality, stability, time shift invariance. System is defined on time space by the difference equation. And the block diagram is actually the implementation, meaning that it shows in which order the calculations are done. And then basically you can optimize the system for smallest amount of calculations possible. Transfer function, it's basically a system description in complex frequency domain. And basically it relates to convolutions so that the linear convolution is the same thing as multiplying the input transfer input z transfer with the system transfer function. Okay, some properties, and then we have this product form of the transfer function when you calculate the roots, meaning zeros and poles of the system. Then you can draw it like that. Okay, and the poles must be inside of the unit circle in order to this system to be stable. Okay, zeros and poles, stability, yes, good. Excellent. All right. Let me go and